Okay, so this next talk is Jason Reich, thinking about advances in Lazy SmallCheck.
Yes, it's another property-based testing talk again. Let's begin with a motivating example. It works, excellent. Let's consider this property. That is to say, all reductions on lists of Boolean values to a single Boolean value can be expressed using a folder. Now, who here thinks that this is wrong?
What is a reduction?
Well, you're all going to be in for a big shock. If those of you do think of a counterexample, please just keep it in your mind. But yes, it is going to be wrong, because otherwise why would I be testing it? It's boring. But there are some interesting things about this property. We have some quantification over functional values. We have an existential quantifier. And we are nesting quantification contexts within each other. So this isn't as small an example as it appears. And I want to test this, so I'm going to look at my favourite Haskell property-based testing libraries, which will be wonderfully explained by Peter. We can do a check where we randomly look through some test data space, trying to find a counterexample to our property. And that's good because that does support functional values, but doesn't support existentials, because if there's only one thing that satisfies your existence, then it's going to be really hard to find it randomly in a massive space. So they just didn't see much point, which is fair enough. But yes, they do handle the rest of quantification for other things. We have SmallCheck, which, like the asked, is systematically searching some space, but we do it only look at a bounded space, so it definitely terminates. So we look for all the small test data values up to a certain size. And yes, that supports functional values, and it supports existentials, and that supports nested quantification, which is good. But it's not quite as sexy as Lazy SmallCheck, which also searches a bounded test data space, but it includes partial values in that test data space and uses that to guide the search. It's this demand-driven stuff, which would be great if it supported any of the features we needed for that property.
Just a question, but if you can nest quantifications and also in like a left-handed function, you kind of encode existentials.
You're absolutely right, but I'll do it more complicated later on.
Okay.
So right. That's good. So for the moment, I guess we're just going to have to stick with SmallCheck. And we encode our property, as you saw above. We say test this property, and oh blimey, I thought it was meant to be small. We're looking for minimal examples, right? Actually, when you get into it, it's not so bad. It's actually just R is the function that doesn't want false in the list, which is fair enough. And yes, all right, I guess when you put that into the property, yes, that would falsify it because you can't represent that with the fold R, but it doesn't really tell us much about it. We were wondering whether we could do better, and to be honest, we do like Lazy SmallCheck, so we thought we should try and bring some of these features to it. But I guess I should go into what Lazy SmallCheck is in a bit more detail. So, Lazy SmallCheck. The check means that it's a property-based testing library, so it can easily recognise its existence. The small means that we are, yes, exhaustively searching for a minimal counterexample in some bounded space, because if there's a big counterexample to our problem, there's probably a smaller one which will be easier for us to play with. And the lazy is what describes the fact that we're including partial test data values in our space, and we are using the evaluation order of our property to guide the search through the space. What's the benefit of this? So, all right, let's take this example up here. So, let's look at inserting a value into an ordered list and whether this maintains the ordering over the list. So, we'll test this to some depth 7 in SmallCheck, and it takes 100,000 test data to clear the space. which is good, but if you notice down here, it's saying, well, most of them didn't satisfy our initial precondition anyway. So that's a lot of wasted effort. So what Lazy SmallCheck does, it only checks about under 2,000, which is a tiny fraction of the original space that there was there to search. And it does this, like so, using this lazy precondition. When we get to something like the list that begins with 1 and 0, we know it's going to fail this precondition. And because of that, we know all of these sorts of values that are just instances of the above one don't need to be tested. So Lazy SmallCheck just throws them away. In fact, we haven't even mentioned x yet, because we haven't reached it yet. So from that, for these sorts of x's, we never really generate any value of x beyond undefined.
Wait, how do you know you understand? I mean, you need to know what is order of this document.
But don't forget, in the lazy language, the order, when we're applying this, the evaluation order is coming through free. So the way that we're doing this is by passing exceptions through and seeing whether they come out or not. If you want to learn more about this, I suggest you check Colin and Matt's original paper. So, as I said before, what we want to do is bring these features along to Lazy SmallCheck. On top of that, we can give a better display of counterexamples than Lazy SmallCheck had originally. And if you buy now, I'll even throw in performance speed up. So, go back to our original motivating example. All reductions on list of booleans to a single boolean value can be represented with a fold R, though it can't. And it gives us this lovely tiny counterexample, which is the function that tests for multi-item lists. And one of the nice things you get from this is using wildcard patterns, which the previous one just didn't have a concept of. And secondly, actually, we're not even interrogating the elements of the list at all. This is even more polymorphic property that doesn't hold over reductions to a single value, which is quite nice. So, let's talk in detail about some of these new features that we've brought over to Lazy SmallCheck. I'm afraid this is quite a convoluted example, but it was the best one I could think of. What this is looking for a predicate over list of booleans, again, because I like my list of booleans, boolean functions. That doesn't satisfy this. It's not particularly pretty, but fair enough. Can it find something? Yes, it does. And if you notice, it's quite small compared to what's up there. And it's a partial function. And once again, we've got these wildcard patterns as well. And these are all just coming through without me having to tell it about it. And the combination of these is what gives us a minimal counterexample. So, as I said, Lazy SmallCheck now generates these partial functions with wildcard patterns. Underneath, these are in fact try data structures, but the user never sees it. All they see is a functional value. The wildcards I've had to explicitly describe in the try, but the partiality of functions is just a mirroring of the partiality of the try, which is quite neat, because it's something that you wouldn't be able to do outside of the Lazy SmallCheck context. There's a little bit of work for the users to do, because they have to describe what the try for a particular argument type looks like, but for most boring Haskell 98 types, I've written a template Haskell function that just does it for them. So that makes it nice and easy. So that's functional values. Next up, I promised you we had a better display of counterexamples. First, we don't know what counterexamples sort of look like in the original Lazy SmallCheck. So this function here is looking at, how best to describe it? If I apply a function using fold L1, it should be the same as fold R1. And we know that's not true, so right, let's focus it down, just say for the function that ignores the first arguments and just inverts the second argument. And it comes out with a counterexample and it says if I gave folder L1 const not this list and folder R1 const not this list, they wouldn't be the same, which is true. But once again, I mean, we're getting too much information here. In fact, I mean, it's not helping us target down why this property isn't true. So, the issue was that it's displaying the way that Lazy SmallCheck originally worked was it just, even though it may falsify on a partial value, it then has to force the first totally defined count, for example, in order to display it. What we've done now is we've allowed it to have some representation of the partial data value. And the way that we do this, jumping myself too far, getting nervous, is by using Nice's technique of chasing bottoms. So by carefully forcing and expanding various bits in a generic way, we can display things that, yes, do have exceptions inside, which is useful. And I think this gives us more information about why that property fails. All right. How about these quantifications? So I promised you earlier we'd have a more complicated one. So think of this as sort of a property of scholomization. So if I have some relation R over a binary relation over piano numerals, there must exist some function such that for all x's in the domain of the relation, I must be able to satisfy the relation using this function. And we'll run it, and I've turned on timing statistics so that I can see how long it ran. Jumping ahead myself. And it takes about a minute to check over a pretty large space of functions. And just to stress, I mean, if I was to run this in SmallCheck, I mean, in that time, I don't even get to depth 3, let alone depth 8, because there are lots of things that can be pruned away using this lazy pruning principle that just never needs to be checked. So as I promised earlier, so we've got a quantification nested inside the left-hand side of the equivalence operator, which is something that you wouldn't be able to just lift out. Does that make sense? Alright, so yes, that's quite a complicated one, with quantifications nested inside the property language. So, what we've brought in is these extra for all and exists combinators to our property language. And what we've shown is that lazy pruning is actually quite beneficial for extensions for the same reason it was for universal quantification, because you can search for that one value in a smaller space if it's being pruned away. In order to implement this, however, we need a real rethink of the underlying architecture of Lazy SmallCheck, because it just wasn't possible in the way that Matt originally encoded it. Which brings me to the evaluation, how this compares to the previous version. So as I said, we had to completely rewrite the underneaths. And somehow, despite the fact we made it more complicated, we made it much faster. We're still not entirely sure why. The theory is that Matt's implementation had to serialize and deserialize data structures at various points, whereas I didn't quite understand it, so I didn't do it. I think I must have just fused that structure away in my head. And so, yes, most of our examples here, so numbers less than 1, say a speed improvement over Lazy SmallCheck of yesteryear. There's a few that are either the same or slightly increase. They are still under investigation. It could be because in the original Lazy SmallCheck there wasn't much serialization going on. Now, you know, despite the fact we removed it, we've added extra overheads and things like that, but we're still investigating, hoping to have that in the final paper. But, I mean, that's good, right? Funnily enough, I'm not the only person who's been thinking of functional values in property-based testing this year. Ken Heisen has also been writing up work I think he did a few years ago, to be honest. But he's been extending the functional value generation, functional value capabilities of QuickCheck. So he also uses tries, but not to generate the values, but then to be able to show them to to the user when a property, for example, is found, and shrink them into smaller counterexamples to make things easier for people to understand. The way that he's implemented it, the user doesn't get exposed with a pure Haskell function for their properties. It gets wrapped up in a modifier which they then have to unpack into being the functional value they want. So there's a little bit of pludge over the top. But it's all interesting stuff. In fact, so interesting that one of the things I'm working on is trying to take his tribe representation, because it's a lot more elegant than mine, and implement it in our framework so that we can share argument instances between them. Unfortunately, at the moment it seems to be difficult to judge when I say that a function exists at a certain test data depth. It's harder to determine with his implementation. So that's still work undergoing. The other thing we're looking at is, this should be an embarrassingly parallel analyzable job, because we're looking at massive amounts of data and doing the same operations each time. So we thought we'd give it a go the naive way, just by sticking a par map into an important part of the algorithm. It worked. I mean, I say it worked. It worked for everything where all spaces where you don't find a counterexample, we get the lovely, near-perfect speed-ups that you only get in your dreams. But if it's a space that does have a counterexample in it, it slows down. It's weird. Any parallelization experts, I'd love to chat this over with. So, to tidy up, SmallCheck's handling of functional values was less than satisfying. So we decided to bring it over into Lazy SmallCheck, and it showed that the laziness actually has benefits to functional values in partiality. Displaying counterexamples also somehow gives us more information than a totally defined one, despite showing us less bits, which is pretty useful. Existentials also benefit from being in the lazy context, and for some reason making my algorithm more complicated made it faster. But we've introduced a broader range of functionality, and we're currently looking for good applications of it. So thank you very much.
Any questions?
Yes.
So, it's a question about the semantics of existent for all. So it's a small check, so for all is just trying to enumerate all the cases, and exist is also trying to enumerate all cases and find.
You know the conversion between for all and exist, like not things like that. So it's basically doing that. And in fact, it's looking for the first counterexample.
So no special magic in this.
No. It's just, the issue is in quick check, you wouldn't find it, because you're searching around in space where there might just be one thing. Any questions?
Any more questions? Okay, well, so your checks were all first order, fixed order, higher order.
Yeah, so the thing that I glossed over there was that all the functional values I had there were first order functional values, and we just can't do it for higher order functional values. I think there's a theoretical problem there, but I don't have it written down yet. So that's the reason why all the examples were quantifying over first order functional values.
Anything more?
Yes.
I noticed that all your examples are Boolean values. Boolean leaf elements. You said select Booleans. So is there other elements of that?
Just because it's quick to show on the screen, there's only two things to compare, so it
So
goes
that
into a
will
slide.
make your generation faster if you have a larger data type.
Yeah, it's true. It's just, it was for display purposes. We handled pretty much all Haskell 98 data types.
Okay, thank you very much.
Thank you very much.